And the thing to notice is that we can always isotope such an embedding around until it intersects the 2 handle in a collection of these parallel copies of the core. And so this gives us sort of a natural idea of how to talk about the complexity of these spheres. We just ask, what is the minimum number of cores that we see when we intersect the sphere with the 2 handle minimized over the entire isotopy class of the embedding? Okay, so that's essentially what's captured in this definition. So for an n-shaped slice not K, we take the minimum number of those intersections, we subtract 1 because that removes the algebraically essential copy of the core, and then we divide by 2 since we're really counting sort of algebraically canceling pairs of cores. You'll notice that the green cores are sort of all oriented one way and the orange core is oriented backwards. And so you sort of have an essential green core and then a bunch of green-orange pairs. Okay, and then the thing to note is that if this number is 0, that says that there's just 1 green core, which means that your 2-sphere intersector 2 handle is a disk, which means the portion that intersects the 4 ball is also a disk, which means you're not with slice, and vice versa. So this is somehow maybe like the right notion of complexity. So now we ask, are there high complexity shake slice knots? And this is the main result. So for each non-zero framing and each complexity you could be after, there is an explicit n-shake slice knot, which I can construct for you, whose complexity is bounded below by your choice C. So here's roughly how you build them. So the knots K and C are satellite knots, which we've seen already in Claudius's talk. We have these 2 satellite patterns, Q and Q slash. Composition and exponentiation there, that means repeated composition of the satellite operator. So actually, this satellite knot has 2C essential tori in it. And so the crossing number is going to be the crossing number of Q raised to the C power times the crossing number of Q slash raised to the C power. So you're never going to draw a practical diagram of these things. We then have this lemma, which is given by sort of a very easy geometric argument that says smooth 4-ball genus bounds complexity from below. And so you might think, well, okay, that just means we can compute one of the many well-known concordance invariants that bounds genus. But the problem is our assumption these knots are n-shaped slice causes most of these invariants to vanish, which is what makes this problem kind of challenging. On the other hand, the Levine-Tristan signatures for sort of miraculous topological reasons don't have to vanish. And so if you've never seen this before, this function sigma, it's a map that takes in a unit complex number, a unit norm complex number and a knot and spits out an even integer. And that integer gives a lower bound on 4-ball genus. And so in particular, the main technical result of this work is for each knot K and C, finding a critical unit norm complex number at which the signature of K and C is exactly what we need it to be to get the lower bound. So that's what we do. We do more matrix algebra than I care to admit in order to find this value T crit. And at that value, when we compute our signature, we get our bound and we get our theorem. So part of the reason I'd like to talk about this at this conference is that if some of the folk in this room and the TQFT community as a whole can give us sort of good methods for computing S of knots of this form, so iterated satellite knots, then there's an immediate application, which is an exotic version of this theorem. So if anyone's working on that and they get anywhere, you should send me an email and we will write a paper together. So now let me show you very quickly what the patterns Q and Q slash are. This is the pattern Q. As you can see, the crossing number is high, but the winding number is 1 and the wrapping number is 3. So maybe not too far from what Claudius was talking about yesterday. And then here's the pattern Q slash, also winding number 1, wrapping number 3. So you can see and notice this is where the dependency on the framing comes in. So thank you very much for listening.
Thank you. So let's have just one question and leave the rest for the lunch. Yeah, go for it.
I read a very good paper of Lisa Piccirillo and Allison Miller on dualizable patterns. And then I messed around with, so you can, both of those patterns are dualizable. And then you need them to have a specific type of Seifert surface in order to compute the signature. And so it was a matter of sort of tinkering with the way that one builds dualizable patterns in general until you find one that has the appropriate Seifert surface and then therefore a computable signature.
Thank you. And, you can also full screen.
Okay, that's sure.
Okay, our next speaker is Fraser Bin from Boston College, and he's going to tell us about links with Kovanov homology of low rank and rank bounds in not-floor homology. Go for it. Thank you.
So thank you very much for the opportunity to speak. Yeah, I'm here to talk about some joint work with Schwankar Day. So given a link invariant like Kovanov homology, there's a sort of natural class of questions you could ask of the form: if you have Kovanov homology of a given type, which links can have Kovanov homology of a given type? And this is called the botany question, and we'll be interested in a particular version of this question, namely what links have Kovanov homology of low rank. And so maybe just for context, I wanted to make the following remarks. So that is that if you've got an L component link, then the rank of Kovanov homology is at least 2 to the power L. And this essentially follows from sort of the fact evaluating the Jones polynomial in 1 gives you -2 to the power L. And of course, Kovanov homology categorifies Jones polynomial. Okay, so with that in mind, our result is sort of related to this question. So what we can do is, if we have links with Kovanov homology at rank 8, we can classify them. So they have to be one of either unlinks for most free components, a hop link, a trefoil, T2 plus or minus 4, or a hop link disjoint union non-plus. And so this result was sort of originally due to Zhang and Xie in 2020. I guess their proof uses sort of instanton stuff. We have a different proof, which I'll talk more about now. So the main sort of technical tool we use is Delin spectral sequence, which relates Kovanov homology and not-floor homology. And you can essentially think of this as like a lower bound on the rank of Kovanov homology in terms of not-floor homology, for the purpose of this talk. So I guess I should say a little bit about not-floor homologies. This is an invariant of links due independently to Oswald Sabo and Jacob Rasmussen, and takes value in the category of braided vector spaces, much like Kovanov homology, but unlike Kovanov homology, it's sort of defined using symplectic topology and analysis and Higger diagrams. So here are a couple of facts that we use in our proof. So if L is a link, then the sort of maximum grading of not-floor homology is determined by the number of components of L, and the Euler characteristic of L in this way. Moreover, there is some sort of bounds on the rank of not-floor homology for non-fibered knots. So if you've got a non-fibered knot, then you know that the rank in this maximal Alexander grading is at least 2. And so what we want to do is we want to find a sort of lower bound on the rank for sort of fibered knots as well. And so we do this by passing through some discussion of braids. So for us, a braid is a triple consisting of a surface, a diffeomorphism, and some points. And this diffeomorphism fixes the boundary pointwise and permutes the points. And so I guess I like that picture of these. So here I've sort of taken the surface and I've thickened it and sort of drawn arcs corresponding to these points. And I imagine sort of gluing the top of the surface to the bottom, top of the thickened surface to the bottom of the thickened surface. And when you do this, what you can do is you can sort of construct nice Higger diagrams of the type shown on the right. And when you have these nice Higger diagrams, well, what Baldwin, Velvik, and Berteshi can do is they can define an invariant called the Braid Invariants, which takes value in the not-floor homology of the braid closure. And maybe I should mention this is this braid invariant is sort of based on work of Honda, Kazes, and Matic. So what do we do with this? Well, Led, who I think is going to be a postdoc here next year, has a result which shows this braid invariant is non-zero under appropriate circumstances. And what we can do with Lev's result is we can then produce another collection of generators. In particular, we can find from Lev's generator, we can find another L distinct generators. And so this is our sort of key tool in proving the following, which is sort of a result for not-floor homology. So what we can do is we can find all links with not-floor homology of rank 8. So these have got to be an unlink, or a T2 plus or minus 4, or again, the Hopf link disjoint being the unknot. And I guess I've stated this result for the rank 8 case, but we have similar results for rank 6 and 4 and 2. And if you combine all of these with Dowlin's spectral sequence, you can recover exactly the result I stated at the beginning. So this classification of links with Kovanov homology of low rank. Okay, so I think I'll stop there. Thanks for listening.
Questions? So let's leave the longer questions for lunch and thank Fraser again. George, are you ready? First. I should have checked with you. And he's going to tell us about associating Lagrangians to tangles via the Chern-Simons bundles. And I forgot, he's from Indiana University. Thank you.
Thank you. Yeah, so I want to thank the organizers for giving me the opportunity to talk here today. And thank you all for being here to listen. So yeah, I'm going to talk about associating Lagrangians to tangles via the Chern-Simons bundle. So this is kind of a weird thing where we're going to take a tangle and I'm going to show you how to associate maybe a Legendrian knot to it in some other manifold. Yeah, without further ado, we're talking about tangles. This has been a common theme this week. So just in case you don't know, a tangle is just giving a 3-manifold of boundary. A tangle in that 3-manifold is a properly embedded, smooth, one-dimensional submanifold. Typical example is up on the screen behind me. And we're going to be interested in taking complements of tangles. And so if I were to remove a little tubular neighborhood of my tangle, just of the strands, I would obtain a new 3-manifold with boundary, where the boundary is now a union of a punctured surface and a bunch of annuli. So try to indicate that on this picture here. If I remove a little neighborhood of this 2-stranded tangle, I get a 3-manifold whose boundary is the union of this orange annulus, this blue annulus, and then this black 4-punctured sphere on the outside. What you can see here. So it's important that the boundary is made up of a union of a punctured surface and a bunch of annuli glued to it. Okay, so somehow we're going to get a Legendrian submanifold. Where's that going to come from? Well, first we're going to start with the symplectic side of things. So there's something called the traceless character variety, and it works like this. Basically, it assigns to a pair of a 3-manifold and a tangle in it a stratified symplectic manifold, whatever that means, and an immersed Lagrangian submanifold in that symplectic manifold. You don't have to worry about the stratified adjective too much. Just think of the symplectic manifold. But the point is, if I give you a tangle in a 3-manifold, I get a symplectic manifold with an immersed Lagrangian inside of it. So what is a traceless character variety? All it is if I give you a punctured surface, then the traceless character variety for that punctured surface is obtained by taking all representations of pi1 of the surface into the Lie group SU2. So that any generator of that pi1 corresponding to a boundary component of our surface gets mapped to a traceless element of SU2. So you can make an SU2 as a matrix group. I'm literally just taking the trace of a matrix. I'm asking for elements that have trace equal to 0. And then there's an action of SU2 on the set of these representations by conjugation. We just mod out by that conjugation action, and that's going to be our character variety. We can do basically the exact same thing for the complement of a tangle. Instead, now we're going to ask for generators of pi1 of the complement of the tangle corresponding to meridians of the tangled strands. We're going to ask that those go to traceless elements of SU2. And then again, we're going to mod out by this conjugation action. So I have a traceless character variety for the surface, the punctured surface. I have a traceless character variety for the complement of the tangle. And the traceless character variety for the complement of the tangle maps into the traceless character variety of the punctured surface in its boundary as an immersed Lagrangian. Okay. And there'll be some more pictures in a minute, but before we get there, we're going to be able to produce these Legendrians using what's called the Chern-Simons bundle. This is an example of something called a pre-quantum bundle. What is it? Without going into details of the construction, it's just a principal U1 bundle, and it comes equipped with a connection 1 form whose curvature 2 form is the symplectic form downstairs on that traceless character variety. So the traceless character variety for the puncture surface is some symplectic manifold I've now put a U1 bundle over that symplectic manifold, and it comes with some special one form on it. Basically, D of it, that's not quite right, but basically D of that one form is the symplectic form downstairs. Not really D, it's the curvature, but close enough. So somehow that connection one form on that bundle is inducing the symplectic form downstairs. And sort of the magic thing about this Chern-Simons bundle is that there's a special section over a traceless character variety, the image of the traceless character variety corresponding to the tangle complement, that basically lifts, as I have a pen here. So this is that Lagrangian immersion here, circled in red. We have a lift of that Lagrangian immersion using what's called the Chern-Simons function. This is why we call it the Chern-Simons bundle. If you don't know what the Chern-Simons function is, don't worry about it. It's just some special function that eats traceless representations. And it turns out that even though it's not actually a well-defined function, it does induce a well-defined section of this bundle, which is kind of a weird thing. And that section is parallel with respect to that special connection on the bundle, which just means the following thing. The fact that we are a parallel section basically means that the lift is Legendrian, because this pre-quantum condition, the fact that curvature of the connection one form is the symplectic form, turns out to be equivalent to saying, or basically it implies that that connection one form is actually just a contact one form. So the total space of this bundle is in fact a contact manifold, and the lift of this Lagrangian immersion is actually a Legendrian immersion. Okay. So the special simplest case would be two-stranded tangle, the three-ball, traceless character variety of the corresponding punctured surface. Well, that corresponding punctured surface is a four-punctured sphere. The traceless character variety of a four-punctured sphere is in fact a pillowcase. A pillowcase, if you've never seen it, is just a two-sphere, but it has like four cone points, four singularities. So I've tried to indicate that with this picture here. You have four little cone points around the edge, so it's not really a smooth manifold. That's the traceless character variety of the four-punctured two-sphere. And if I have any two-stranded tangle in the three-ball, it maps into this pillowcase as an immersed Lagrangian. So you just get some immersed curves basically in the pillowcase. Here's the simplest example. Take this trivial tangle on the left. Its image in the pillowcase, depending on how you parameterize things, is just an arc between two corners of the pillowcase. So it's this blue arc on the right here. Okay. So right, so how do we get Legendrians from tangles? Again, I give you a two-stranded tangle in the three-ball. We are going to be able to lift the Lagrangian immersion coming from that tangle up into this Chern-Simons bundle using the Chern-Simons function, and to give me some a priori Legendrian immersion. Now, I might expect I'm immersing a one manifold and a three manifold. I might hope that maybe generically it's an embedding. You have to be careful about that because of this Legendrian condition and the fact that we are lifting with respect to this very particular section induced by the Chern-Simons function. And so we do some technical tricks, which I'll mention here in just a moment. But my conjecture is basically that under some suitable genericity assumptions, no matter what, you will be able to assume that that Lagrangian immersion actually lifts to a Legendrian embedding, so that I actually get basically a Legendrian knot or a link up in the total space of that bundle. And so here's an example. Again, I haven't told you. So basically on the left here, we've taken that same trivial tangle and I've dressed it up. I've decorated it with some extra stuff called adding an earring, and then something called a Holonomy perturbation. You can ask me what that means later. But the effect is that we turn that single arc into this figure 8 in the pillowcase. So now I have an immersed circle with a single double point. And the result in this case is that that does in fact lift to an embedded circle upstairs. And I guess I'll just mention here at the end that I do have a nice construction for sort of giving this bundle very explicitly in terms of coordinates on the pillowcase, so that anyone here who's familiar with Legendrian knots, say in standard contact structure on R3, you might be familiar with the Lagrangian projection down into R2. And you might know that if you have a parameterization of that Lagrangian projection, you can recover the Z coordinate of the original knot, basically by integrating the contact form over that parameterization. And my claim is I can do the same thing for the bundle over the pillowcase here using some fancy fourfold cover argument. But anyway, I'm going to end here. So I hit the wrong button. But anyway, thank you guys.
Thank you.
Let me see if I stop sharing.